Hello, everyone, and welcome. We are here doing the colloquium series at the Brown Planetarium at Ball State University. We are joined by Tharindu Jayasinghe from The Ohio State University, a graduate student studying astronomy and astrophysics. Um, I'll go ahead and just turn it over to Tharindu and let him introduce himself and kind of give a talk for us.
Yep. Thank you so much, Greg.
Mhm.
Let me share my screen. Give me a second. All right. Thank you so much for having me here. And hi, everyone. My name is Tharindu Jayasinghe. And today I will be talking to you about the search for the quietest compact objects in the Milky Way. So by way of an introduction, I'm a fifth year PhD candidate at the Department of Astronomy at the Ohio State University. And I work with Professors Chris Tanek, Chris Kochanek, and Todd Thompson on the all-sky automated survey for supernovae on a variety of topics, including variable stars and compact objects. All right, so let's get started. So going over my talk today, I will first give an introduction to motivate our search for non-interacting compact objects. Next, I will talk to you about how we can actually find them. And I will finish by discussing two examples of non-interacting compact objects that we discovered in the last couple of years. All right, so when it comes to studying stellar mass black holes, our story starts with massive stars in the Milky Way. These are stars with masses larger than about 8 solar masses. So as illustrated by this figure here, stars like our sun evolve very differently when compared to massive stars. Low to intermediate mass stars evolve to become red giants, and then they leave behind white dwarfs. On the other hand, massive stars, they evolve to become red supergiants, explode as supernovae, and then they leave behind neutron stars and black holes when they die. So because they are the progenitors of black holes, we will only focus on massive stars for this talk. Massive stars play a crucial role in the evolution and structure of the interstellar medium in galaxies, and they also contribute significantly to their nucleosynthesis. While they are important in many ways, they are short-lived, with main sequence lifetimes in the order of a million to a few million years. And on an astronomical timescale, they evolve and quite literally go out with a bang in the blink of an eye. So one of my favorite images of massive stars doing exciting things is this panel from Adams et al. 2016, showing the disappearance of a massive star in the galaxy NGC 6946. So it is thought that the star underwent something called a failed supernova event. It brightened momentarily before it completely disappeared from optical wave. So the left panel shows what we saw with the Hubble Space Telescope in 2007. And on the right, you see the same field in 2015. So this star just went away. The current hypothesis is that the massive star underwent a co-collapse event, resulting in the formation of a stellar mass black hole. So we know that when massive stars die, they leave behind compact remnants, such as neutron stars and black holes. However, it is very difficult to pin down their final fate for any given massive star. Many groups have been working to tackle this question by quantifying the so-called explodability of these stars. The idea is that more massive stars that explode leave behind a neutron star, whereas those that implode collapse to form black holes. A good metric to define this explodability is something called the compactness parameter, or Xi 2.5, shown in this plot here, which characterizes the innermost 2.5 solar masses of the star, and it is evaluated when the collapse speed of the star exceeds about 1,000 kilometers per second. This is the theoretical measure, but it is very useful to understand the landscape of compact objects that remain after massive stars die. So this plot on the left shows how this parameter varies with the mass of the star before it goes supernova. Stars below about 15 solar masses have a very small compactness value, and they're very easy to explode, whereas stars from about 22 to 26 solar masses are much more difficult to explode. Beyond about 32 solar masses, the effects of mass loss through winds start to come into play, And this parameter is about constant for these very high mass stars. And on the right, this platform Patton and Sukhbold show various massive star models evaluated on the basis of these three different prescriptions for compactness, including the Xi 2.5 parameter. So what you have to take away from this plot is that stars with smaller compactness are easier to explode than those with higher values. Okay, so how does the framework of compactness and explodability help us to understand the landscape of compact remnants? Let's focus on this plot by Sukhbol et al. On the left to try and answer this question. The results of 5 different supernova engine models are shown in order of the strength of the engine, with the strongest at the top. The final fates of these massive stars with various pre-supernova masses are color-coded. In a lot of cases, exploding massive stars leave behind neutron stars in green. In some cases, these explosions also create black holes through something called fallback, shown in blue. When the massive stars implode, they create black holes, shown in black. So we see that the final fates are very complicated and they don't follow a simple relationship with the pre-supernova mass of the star. And this picture is much more complicated by binary interactions that occur while the stars are still alive. This plot on the right shows how the mass of the compact remnant depends on the mass of the carbon-oxygen core. As you can see, there's a significant difference when binary interactions are also considered. So while what is clear for us from these studies is that while we know that massive stars can create neutron stars and black holes, their final fate is very hard to predict, and it is dependent on many things, including supernova physics and binary interactions. So as I said before, it's very difficult to do this, but many groups have attempted to predict the compact object mass distribution. In this slide, I've shown mass distributions from 2 different groups. So the left plot from Fryer and Calagrera focuses on the mass distribution for all compact objects, including neutron stars. The different lines correspond to different power law indices for the initial mass function. Here we see that most of the compact remnants that are left behind are neutron stars, with masses about 1.4 solar masses. This is also true of the more recent work by Woosley and collaborators. Neutron stars are heavily peaked at around 1.4 solar masses. But what does the picture look like for black holes? Here, I will focus on the more recent work by Woosley et al. The median mass of black holes in this work is about 9 solar masses. More massive black holes are also predicted. Here, we see a nearly constant slope in the black hole birth function between about 15 and 35 solar masses on the plot on the bottom right, but the distribution is more complicated elsewhere. As I showed in the previous slide, stars frequently explode below 15 solar masses, and this complicates the final fates of these stars. Above 35 solar masses, mass loss and pair instability supernova come into play, and it makes this prediction much more uncertain. So this is a very important work that helps us understand the landscape of compact objects in the Milky Way. This can also be tested and constrained with observations from electromagnetic techniques and now gravitational wave observations. So a point I touched on earlier is that binary interactions have a significant impact on the evolution of massive stars. This figure from the gravity collaboration on the left illustrates how the multiplicity fraction varies with the mass of the star. Essentially, we see that nearly all massive stars are in binaries or higher order systems. This means that it is very crucial to understand binary interactions and how they affect the lives of these massive stars. This classic figure from Sana et al. Shows that about 70% of massive stars are affected by binary interactions, which include mergers, common envelope evolution, and envelope stripping. So binarity is also very helpful when it comes to searching for and finding the compact remnants of massive stars. If the compact remnants are in bound binaries with a luminous companion, we can try to find these electromagnetically dark compact objects using their companion stars. So compact objects in binaries, that is the theme moving forward. So I think it is clear that our Milky Way is swarming with neutron stars and black holes, and some of them may be in binaries around other stars. To put some numbers into context, there are an estimated 10 to the 9 neutron stars, so about a billion, and about 10 to the 8 black holes all over the galaxy. To understand their formation and their mass distribution, it is of interest for us astronomers to search for these compact objects. So using the discoveries of compact remnants from electromagnetic methods and gravitational wave observations, we can now take a look at the observed compact object mass distribution instead of the theoretical one. This excellent plot illustrates the masses of the compact objects from both electromagnetic discoveries and LIGO-Virgo discoveries. For the LIGO-Virgo events, the masses of the pre-merger compact remnants are shown along with the resulting mass of the merged object. This shows the awesome impact of gravitational wave observations to this field. For example, we have made many discoveries of high mass stellar black holes thanks to LIGO. Another topic of interest is its apparent low mass gap between the most massive neutron stars, observed with about 2.1 solar masses, and the least massive black holes with about 5 solar masses. Here, I visualize the mass distributions inferred using three methods: gravitational wave events, X-ray binaries, and microlensing. The top panel from Tiwari and Fairhurst shows the component mass distribution from gravitational wave events. Here, they find an excess of black holes at masses of about 9, 16, 30, and 57 solar masses. The bottom panel from Ozil et al. Shows the mass distribution of X-ray binaries. Here, they find a strong peak at about 8 solar masses, and they also noted a dearth of black holes, less massive than about 5 solar masses. The bottom right panel from Rose et al. Shows the mass distribution of compact remnants inferred from microlensing events. Here, they claim that they don't have evidence for this low mass gap between neutron stars and black holes. It is clear that the compact object mass distribution is complicated, but there are some features that match the theoretical predictions. For example, the median peak at about 8 to 9 solar masses is seen in both observations and in theory. Nonetheless, we need more mass measurements to better constrain the observed distribution. So how have we discovered compact remnants that are used to study the observed mass distribution? Well, some of these compact objects are relatively easy to find. For example, the neutron stars and black holes in X-ray binaries are bright X-ray beacons that can be promptly identified using X-ray telescopes. Other discoveries have come from pulsars that are discovered in radio observations, and more recently, merging compact objects have been identified through gravitational wave observations from LIGO and Virgo. However, most compact objects are much more difficult to find. This is because these non-interacting black holes and neutron stars are electromagnetically dark when they are in quiescence and are not interacting with companion. What does this mean for us? We have barely touched the surface when it comes to the discovery of these objects. As illustrated using this image of an iceberg, our current census of compact objects is a very biased sample. This is because this sample only probes a very narrow range of parameter space in orbital properties, for example. To put things into context, there are a few tens of known stellar mass black holes out of an expected count of 10 to the 8 such black holes in the Milky Way. So what we are really seeing here is the tip of the iceberg of compact objects in our galaxy. Clearly, there are a lot of discoveries that can be made, which will enable us to understand the formation and distribution of compact objects in the Milky Way. So I've shown this plot to illustrate the biases in the current census of compact objects in the Milky Way. Here, I have plotted the mass of compact objects against the orbital period of the host binary. The black points come from dynamical mass measurements from the Watchdog catalog. Most of these systems are low mass X-ray binaries. It is clear that most of these systems are in short period binaries. This is of course expected, as these are interacting accreting systems where the luminous companions fill their Roche lobes. There are a few compact objects in binaries with orbital periods greater than about 10 days. But does that mean that these binaries don't exist, the ones with long periods? Of course not. We just haven't found them yet. And this is what the same plot looks like with recent discoveries of non-interacting systems included. The blue points are discoveries from a long-term radial velocity study of the NGC 3201 cluster conducted by Jesus et al. The red circles are the discoveries of non-interacting compact objects in the galactic field. The sample size is very small, but I think it is clear that there are many long-period non-interacting compact objects in the galaxy. Also of note is that some of these non-interacting systems have compact objects in the so-called mass gap. So we really need to keep filling this plot to better constrain the black hole mass distribution. By the way, these three circles are discoveries made by our group at Ohio State. I will discuss two of these systems today, and the third object is still being followed up as of right now. Okay, so we know that many non-interacting compact objects exist in the Milky Way, and it is of interest to find them. But the question is, how do we do that? All right. So the discovery space for non-interacting compact objects is opened by radial velocity searches, photometric monitoring, and astrometry. There is a good overlap between these techniques. So the best approach is to rely on more than one technique. Today, I will briefly go over two of these techniques, the radial velocity and photometry methods, and how they can be used to search for compact objects. Okay. The first technique is the radial velocity method, where we use spectra to look for Doppler shifts in the absorption lines of the stars in order to calculate their radial velocities. If we have more than one spectrum per star spaced out over time, we can look for variability in the radial velocities. If we see radial velocity variability in the data, that is a good sign that the star is in a spectroscopic binary. This method is also very popular with exoplanets, but unlike exoplanets, it is much easier to look for Doppler shifts caused by massive companions like black holes and neutron stars. While the radial velocity amplitude caused by an exoplanet companion can be as small as a few meters per second, we are looking for radial velocity amplitudes larger than a kilometer per second. Most of the time, the radial velocity amplitudes for compact objects in binaries is upwards of a few tens of kilometers per second. So if we have enough radial velocity epochs, we can derive spectroscopic orbits for binary systems. And we can use this information to determine the mass of the companion. In the last few years or so, this method has become very popular to search for binaries, and not just the compact kind. This is largely thanks to the advent of large wide field time domain spectroscopic surveys like Apogee, LAMOST, GALA, and RAVE. Collectively, they have built a massive dataset with spectra for more than 10 million stars in the Milky Way. This is truly incredible, and it has led to many awesome results in the fields of galactic chemical evolution and astroseismology, to name a couple. These surveys sample stars from all over the sky and from various spectral types. To highlight this, shown here on the right, Apogee Spectra for stars of various spectral types. On the left, I've shown the sky footprint of the LAMOS survey and their targets. So how do we use this method to identify compact object hosts? Okay, so as I mentioned previously, we look for radial velocity variability. We need at least two different observations to look for this variability. Fortunately, many of the stars surveyed by these projects have at least two separate observations. This gives us a starting point to pick out RV variable sources from the massive datasets amassed by these surveys. The next obvious step is to look at the spectra themselves and see if we can identify the presence of a second set of absorption lines. A lot of work has gone into the automated identification of these double-line spectroscopic binaries, or SP2s, in these surveys by various groups. In this figure, I've shown a pseudo HR diagram for stars in the Apogee survey from Mazzola et al. 2020. On the right panel, these stars are colored by the maximal radial velocity change observed in Apogee. This ranges from a few tenths of a kilometer per second to a few hundred kilometers per second. So this is an excellent data set to actually go in and look for non-interacting systems. And we have been using this very heavily for our projects. For the compact object enthusiasts, clear SP2s are a big no. We are only interested in the systems that are single-line spectroscopic binaries, or SB1s. What we're essentially trying to do here is to estimate the mass of the companion using the binary mass function. I've shown it in its most basic form here, assuming circular orbits. To calculate this, we need to know the radial velocity semi-amplitude k and the orbital period. Large radial velocity variability is a good indicator of a large binary mass function, and high binary mass functions imply more massive companions. While datasets from spectroscopic surveys give us a good idea about the RV variability and hence an estimate of this semi-amplitude K, it is very difficult to constrain the orbital periods for these systems with just a few sparsely sampled RVs. Of course, there are some systems with enough RV epochs to constrain the periods, but the vast majority actually don't do have that. This is where we need to look at photometric surveys. A huge theme in my work is the overlap between massive datasets from photometric and spectroscopic surveys. I use these data in concert to look for non-interacting compact objects. You will see this theme emerge when I discuss our discoveries, but this is an important point I want to leave behind. There's a lot of utility in combining datasets for more than just a single survey. All right, so let's talk about photometric variability now. In short, photometric variability has got to do with how the brightnesses of stars change over time. As I mentioned before, we need to lean on wide field photometric surveys to obtain an estimate of the orbital periods for the candidates that we identified in the spectroscopic datasets. Fortunately for us, we are in the golden age of time domain astronomy right now. There are numerous wide field photometric surveys operating at the moment, including ASAS-SN, where I'm a team member, Atlas, TESS, and ZTF that generates massive datasets that can be used to study the variability of Milky Way stars. For example, ASAS-SN observes about 100 million stars brighter than the 18th magnitude in the G-band. Collectively, the surveys I've named observes about a billion stars in the Milky Way. In the near future, the Vera Rubin Observatory and the LSST survey will also contribute significantly to these datasets. The idea is to use the datasets from all these surveys to study the variability of candidate compact object binaries that we identified from the spectroscopic datasets. In fact, we can actually do more. We can independently identify good candidates from just the photometric variability and then follow them up with spectroscopic observations. So it's like the kind of the reverse process. Broadly speaking, we can only estimate the orbital periods for certain classes of variable stars. First, spotted stars in binaries that are tidally synchronized directly give us the orbital period of the binary. This is because in synchronized binaries, the rotation period of the star is the same as the orbital period of the binary. Ellipsoidal variability is another popular method to independently identify non-interacting binaries. For ellipsoidal variables, we can obtain the orbital period directly from the photometric variability. For certain configurations of compact object binaries, we may also see a self-lensing effect. This can also give us the orbital period of the binary directly. I included microlensing here because microlensing events can also be used to search for compact objects. Isolated compact objects passing in front of a background star can lens the starlight. Thus, this is also a promising method to look for isolated non-interacting compact objects. Before I move forward, I wanted to briefly talk about ASAS-SN, the time domain survey that I'm a member of. ASAS-SN is a wide field photometric survey consisting of 20 telescopes worldwide. We monitor both the northern and southern hemispheres on a roughly daily cadence. In the G-band, we are sensitive down to about the 18th magnitude and have good light curves for about 100 million Milky Way stars. ASAS-SN uses small telescopes, and therefore we can observe bright sources up to a saturation limit of about the 11th magnitude in the G-band. This is not possible for some of the bigger telescopes due to the saturation limits. This means that we have an excellent overlap with spectroscopic surveys, as they also focus on relatively bright stars. For example, over 97% of the sources observed by the Apogee survey have very good ASAS-SN light curves. And when I say all sky, we are truly monitoring the entire visible sky, as shown by this plot here. Over the years, we have gathered thousands of observations in each field observed by ASAS-SN. To date, we have taken more than 5 million observations in total. So a good chunk of my time as a graduate student was spent characterizing the stellar variability of over 60 million stars in ASAS-SN. Long story short, we came up with a homogeneously classified catalog of over 660,000 new variable stars, out of which 220,000 were brand new discoveries. These new discoveries are illustrated in this plot. And as you can see, we discovered many new variable stars all over the sky. This catalog of variable stars provided an excellent starting point for our search for non-interacting compact objects. A very good example of this was recent work by Dominic Rowan, another graduate student at Ohio State, who used the catalog of ASAS-SN variable stars I created to look for ellipsoidal variables. He identified about 200 of these systems, and here are some example light curves from our paper. We are currently following up some of the most promising candidates for compact object hosts using this list, so there's more to come. All right, finding candidates is just the first step, but there's a lot of work involved in confirming and characterizing these systems. Once candidates are found, we need to use a multi-wavelength approach to confirm them. For example, this might include getting UV observations to rule out the possibility of a main sequence companion, or getting high-resolution optical spectra to characterize a stellar component. In my own work, I've used instruments like the Pepsi spectrograph on the Large Binocular Telescope, the HIRIS instrument on the Keck telescope, Swift observations, and information from the Gaia astrometric solutions. I will go over the importance of follow-up observations in the next part of my talk. So moving on to the next part of my talk, I will summarize two discoveries of non-interacting mass gap black hole candidates that we made at Ohio State. The first such system I will talk about is the black hole giant star binary that kickstarted our efforts at searching for non-interacting black holes at Ohio State. This binary system is located in the constellation Auriga, and it is a binary in the galactic field. We started this project by looking at radial velocity variables in the Apogee survey. To prioritize radial velocity variables for follow-up, we came up with an estimate of the binary mass function using the radial velocity data from Apogee. The binary mass function, as I mentioned before, gives a constraint on the minimum mass of a companion. While we don't have enough Apogee radial velocity epochs to fit the spectroscopic orbit for most systems, we can estimate the radial velocity semi-amplitude k by calculating the maximal change in radial velocity and then dividing it by 2. For the orbital period, we used the photometric period derived from the ASAS-SN light curves, and then we assumed circular orbits when making the estimation. We visually examined about 200 sources with the largest estimated binary mass functions. This system, which I will refer to as J521, emerged as the front runner. At that time, this was the source with the longest period on our list at about 83 days. J521 is a luminous red giant at about 2.4 kiloparsecs from the solar system. It only had 3 RV epochs in Apogee, which we used to estimate the radial velocity semi-amplitude as about 40 kilometers per second. The mass function estimate was about 0.7 solar masses, which implied that the mass of the companion to the red giant was about 1.7 solar masses for a giant, a typical giant with about 1 solar mass and an edge-on orbit. Then we looked at the Apogee spectra and we didn't see a second set of lines, so this looked like a single line spectroscopic binary. A quick look at the spectral energy distribution, or the SED for this giant, also suggested that there was no excess blue light from another star. All of this information told us that this was a very good candidate for follow-up observations. So we went ahead and did that. The ASAS-SN light curves at that time had a baseline of about 4 years. We looked at the evolution of the red giant's light curve shown on the left figure and noticed some variations in the overall shape of the light curve over the ASAS-SN baseline. So each panel corresponds to a period of about 1 year. This kind of photometric variability is very typical of spotted stars and is caused by the evolution of the spots on the giant's surface. To confirm this variability, we obtained additional multi-band light curves in the BVRI bands shown on the top right figure, and this again confirmed the spotted nature of the giant. If we were seeing ellipsoidal variability, we would have expected to see a light curve which is more like a sinusoid, but this was not like that. So we know that the photometric variations are caused by spots on the giant. And this also tells us that the rotational period of the giant is about 83 days. The most crucial part of this puzzle is the spectroscopic orbit. To actually derive this, we had to go and obtain follow-up radial velocity data from the TRESS instrument at the Fred Lawrence Whipple Observatory. The follow-up radial velocities confirm the estimates that we made from just the three Apogee data sets. The orbital period of the binary is about 83 days, which is the same as the rotational period of the giant. This means that the giant's rotation is tidally synchronized with the binary orbit. And we also find that the eccentricity of the orbit is about 0, which tells us that this is on a circular orbit. With the follow-up data in handy, the next big thing we had to do was actually to estimate the mass of the giant and its companion. Unfortunately, as I mentioned before, we weren't seeing ellipsoidal variability in the light curve. This made it a little more challenging to derive the masses, but it wasn't impossible. To estimate the mass of the red giant, we use single-star evolutionary tracks from the Parsec and MIST models, alongside constraints derived from the Apogee and TRESS spectroscopic observations and Gaia parallaxes. In summary, we believe that J521 is an intermediate mass giant with a best fit mass of about 3.2 solar masses. To obtain an estimate on the orbital inclination of the binary, we can use the measurement of V sin I from the Apogee and TRESS spectra along with the true rotational period of the giant, which we know from the photometry as 83 days. We constrain the inclination or sin I to be about 0.97, which is about 75 degrees. And now we have all the ingredients to calculate the mass of the companion using the binary mass function. So we use the binary mass function, the inclination, and the mass of the giant to estimate the median mass of the companion to be about 3.3 solar masses. The plot on the right shows how the companion mass depends on the mass of the giant on the x-axis and on the orbital inclination shown in these lines. If the inclination is significantly lower, the mass of the companion is driven higher. The estimate of the companion is larger than the maximum mass of a neutron star, and if the companion is a compact object, it would be on the lower mass gap between the most massive neutron stars and the least massive black holes. The other part of the puzzle is to actually go ahead and rule out companions to the red giant that could be main sequence stars. So to do that, we look at the spectral energy distribution, or the SED, shown in this plot here. It's essentially a plot of the luminosity in various filters versus the wavelength. So the black data points correspond to the multi-band photometry, and the red line is the best fit SED of the giant. The blue lines show the SEDs of main sequence companions with various masses. Here I've shown 1.3, 1.5, and 1.8 solar mass models. So we use the SED to place a limit to the maximum mass of a luminous main sequence companion to the giant of about 1.5 solar masses. As you can see on the figure, such a star would be very evident in the overall SED, especially towards the bluer end. Now you may be wondering why some of the bluer data, which are UV measurements, don't agree with the SED fit. We obtained follow-up UV observations using the SWIFT satellite and were able to detect the giant in the UVM2 filter. Time series measurements in this filter showed that the giant varied in the ultraviolet. However, we know that the giant is spotted. Spotted stars are chromospherically active, and recent work has shown that UV excesses are expected from active spotted giants. So the most likely explanation for this UV excess is the chromospheric activity from the giant. Okay, so in summary, this was a fascinating system and a very good learning experience for all of us at Ohio State. We learned that a lot of follow-up data is necessary to successfully confirm non-interacting compact object binaries, and that the best way to do so is to rely on a multi-wavelength approach. Putting it all together, J521 is a non-interacting compact object binary composed of an intermediate mass red giant on a circular 83-day orbit around a likely mass gap black hole. Great. So next, I will talk to you about our more recent discovery of the nearby mass gap black hole, which we dubbed the unicorn. We took many lessons from our previous work, which made our lives a little easier the second time around. So you may ask me,
I felt good about it
why
right
did you
too.
call this the unicorn? To answer that question, it is partly because the system is located in the Monoceros constellation, which translates to unicorn in English, and partly because the system is very unique, as you will learn shortly. So, the system in question, V723 Mon, is a nearby red giant at around 460 parsecs from the solar system. This had previously been classified as a photometric variable, where previous work from multiple groups have identified this as a semi-detached eclipsing binary. Since the giant is very bright at around 8.3 magnitudes in the V band, it had been extensively characterized with radial velocities. In fact, the system is listed in the SB9 catalog of spectroscopic binary orbits. What really stands out from the radial velocity data is the binary mass function for this system. As I mentioned before, the binary mass function gives a minimum mass of a companion based on the radial velocity data. V723 Mon has a high binary mass function of about 1.7 solar masses, much larger than that of J521. What this means is that the minimum mass of the companion around the red giant is 1.7 solar masses. That is, if the red giant had a mass of 0, which is impossible. For an edge-on orbit and a typical giant mass of about 1 solar mass, the companion will have a mass of about 3 solar masses. This immediately raises a question. Is the companion to V723 Mon a black hole? A 3 solar mass luminous companion would be very obvious if we looked at the SED, for example. Because of the high binary mass function and the possibility of a compact object companion to the red giant, we decided to take another look at this interesting system. We also triggered a large follow-up campaign to study this system, obtaining spectroscopic observations from LBT Pepsi, Keck High-Res, in addition to ground-based B-band photometry and UV observations from the Swift satellite. To determine the nature of this photometric variability, we looked at the B-band, V-band, Kelt-R band, and test light curves. It immediately became clear that this was not a semi-detached eclipsing binary. In fact, what we were seeing here was ellipsoidal variability in all of the light curves. As illustrated here in this animation on the left, ellipsoidal variability occurs due to the tidal deformation of the visible star due to the gravity of its companion. This is quite unlike J521, where we were seeing the effect of spots rotating on the giant surface. The telltale sinusoidal signature of an ellipsoidal variable is because the amount of flux from the star changes over the course of the orbit. We see the star side on twice and edge on twice during its orbit, and that's why we see 2 maxima and 2 minima in the light curves. Since we are fairly confident that this system is an ellipsoidal variable, we used binary modeling software to fit the light curves and derived various parameters, including the masses of the components for the system. We used 2 different tools, Phoebe and LC, to fit the light curves using constraints obtained from the Keplerian orbit fit to the radial velocities. We find that the system is on a near edge-on 60-day circular orbit. The mass of the red giant is about a solar mass, and the companion has a mass of about 3 solar masses. Both our tools yield very similar results. Another independent validation of the orbital inclination and component masses came from the radial velocity data. We found out that once we fit a Keplerian orbit to the radial velocities, there were significant correlated residuals. This can be seen in both the figures. In their paper, Masuda and Hirano identified that these radial velocity residuals were a result of the ellipsoidal variability and in how it affected the absorption lines of the giant spectra over the course of the orbit. As shown in the figure on the right, they were able to come up with a model to fit the residuals and obtain similar results for the component masses and orbital inclination. Since similar results were obtained from 2 different methods, we are confident about the masses and the orbital inclination for this system. When analyzing the light curves, we also identified an additional non-stellar source of second light. This is immediately clear when the binary models without this additional light are compared to the data, especially towards the bluer wavelengths. To fit the data properly, we need to consider the second light or veiling. In our data, the B and V bands are the most significantly affected by this veiling. We estimate that 63% and 24% of the total light emerges from this veiling source, the B and V bands respectively. We studied this veiling further using high resolution spectra and confirmed the trend of higher veiling towards bluer wavelengths. However, this second light, it drops off very sharply in the UV. When we looked at the behavior of the second light, it didn't behave like a star would. What this means is the second light most likely emerges from some sort of accretion disk around the compact object. We are currently pursuing additional data using the Hubble Space Telescope to try and study the nature of this veiling or second light. Okay, to recap, we are confident that the mass of the companion to the giant is about 3 solar masses. The next step is to rule out luminous companions. We do this by using both the SED for this system and looking at limits on eclipses. Starting off with the SED, as you can see on the left figure, it is fairly easy to rule out a luminous companion with a mass close to 3 solar masses. The dashed line in the figure corresponds to a luminous star with a mass of about 2.5 solar masses. Such a star would be blindingly obvious in the SED because it's hot and luminous in the shorter wavelengths, but we don't see evidence of a blue hot companion in the data. For this system, we expect to see eclipses of a luminous companion for orbital inclinations larger than about 76 degrees. However, we do not see any eclipses in our multi-band light curves. The figure on the right shows Phoebe models with main sequence companions at various temperatures. If such a companion existed, we should have seen eclipses in the data, as you can see here in this plot. So based on the SED and these eclipse limits, we are able to stringently rule out single luminous companions with masses greater than about 0.8 solar masses and binary companions with masses greater than about 1.5 solar masses. And since we rolled out main sequence stars, we looked at all the possibilities for the companion, including compact objects like neutron stars and white dwarfs. And our simplest explanation is that the 3 solar mass dark companion to V723 Mon is a single black hole in the lower mass gap. The unicorn is in fact the closest black hole observed to date, and it is also one of the smallest. It is clear that the discovery of this system and J521, highlighted here in red, will help astronomers study the formation of compact objects in the so-called mass gap.
Unicorn.
On a side note, there was a lot of excitement surrounding this discovery. For example, our press release was picked up by numerous outlets, including National Geographic and Reuters. The popular science channel Kurzgesagt also featured the unicorn in one of their videos titled "The Largest Black Hole in the Universe." They made an awesome video with lovely animations and graphics, so I recommend you check it out if you have some free time. But perhaps the most awesome thing about this discovery was that it inspired middle schooler Henry Thayer to feature our work in a science fair project. I was interviewed by Henry about our discovery, and he asked me some great questions on black holes.
Wow.
Henry did an amazing job with this project, and as you might have guessed, he ended up winning first place. So good job, Henry. Last but not least, it also brought out some latent woodworking skills in my advisor, Professor Chris Stanek. He was inspired to create this awesome depiction of this binary system, which is obviously not to scale. Great. So this was our second discovery of a candidate mass gap black hole. What made this very exciting for us was that this is currently the closest known black hole candidate. That comes with certain implications. Since we found one such system close by, we should find many more if we increase our search volume. We think that there may be 100 to 1,000 such non-interacting compact object binaries where the companion star shows ellipsoidal variability. So there's a lot of promise in finding black holes with these methods. In fact, I'm currently leading the discovery of another likely mass gap black hole candidate, We hope to get our paper submitted by the end of the year, so please stay tuned. And just before I end my talk, I'm going to tell you about what's next for this budding field. And in my opinion, the sky is literally the limit. In the very near future, we expect to see the Gaia satellite release their catalog of astrometric binaries.
Okay.
This catalog will be enriched with a large number of non-interacting compact object binaries. While we can infer certain properties of these binaries from the Gaia data, I believe that follow-up campaigns are necessary to definitively confirm the status of these binaries as compact object hosts. Through this follow-up, we can also learn more about the companion stars, including their evolutionary stages and chemical abundances. Another exciting pathway for these discoveries in the future will come through microlensing studies, using surveys like the upcoming Roman Space Telescope. Recent work has shown that it is possible to use these surveys to discover hundreds of isolated black holes and neutron stars in the Milky Way. And starting very soon, the Milky Way Mapper and SDSS-5 project will take spectra of more than 4 million stars in the Milky Way, up from about 700,000 in the now completed Apogee survey. Milky Way Mapper will target stars in both the northern and southern hemispheres. It will also target a wide variety of sources, from white dwarfs to red giants, as shown on this color magnitude diagram on the right. A large number of these stars will also have multiple visits over the years, just like with the Apogee survey. And this will provide us with a much larger sample to search for non-interacting compact objects. In the meantime, currently ongoing time domain photometric surveys like ASAS-SN, TEST, and ZTF will keep collecting data and build up time baselines for a large number of Milky Way stars. Newer surveys will also come online, including the Vera Rubin Observatory, or the LSST survey, and the Roman Space Telescope. We will be able to characterize the stellar variability of millions, if not billions, of stars in the Milky Way with great detail and use this to search for hidden black holes and neutron stars. Again, I want to stress that this work is best done with the overlap between spectroscopic surveys and photometric surveys. As the sample size in this overlap continues to increase in the near future, that presents us with more opportunities to find non-interacting black holes. I'm very excited for what's to come, and I look forward to keep making more discoveries of these interesting systems. And on that note, I will end my talk with a summary. So in short, the few takeaways that you take away from my talk are that there are many non-interacting compact objects that are waiting to be found, and we can try and find them using massive data sets from time domain surveys, which can help us ID candidates. But we need a multi-wavelength, multi-instrument approach to actually confirm them. In the end, these discoveries will open up new parameter space in binary properties and help us understand about the compact object mass distribution, massive stars, etc. So thank you so much for your attention. I'm really glad to have given this talk to you. And now I will take questions from the audience. Thank you so much.
Wow. Thank you so much for that talk. We had a lot of good information there. So I'll go ahead and just turn over the questions to the classroom first, if anybody has any from there. I've got a couple written down, but I'd like to see if anybody has any in the classroom first.
Any questions?
Okay, so I will go ahead and ask just a couple questions really quick. So the first one, I'd like to ask, do we always look at the mass distribution for both neutron stars and black holes together, or did that just kind of happen organically due to like the similarities between how they form and stuff like that?
That's a very great question. So when we try and study the mass distribution of compact objects, we group together neutron stars and black holes because they form through very similar methods, as in massive stars going supernova or imploding and then creating neutron stars and black holes.
Mhm.
But there are intricacies when it comes to neutron stars and black holes. So that's why people sometimes try and look at them separately. And we have a good understanding of the neutron star mass distribution because of pulsars. We have found many of them in the Milky Way and have mass measurements for a bunch of them too. So using that, we have constrained the neutron star mass distribution very well. But for black holes, we have only a handful of those systems in the Milky Way with good mass measurements. And that makes it much more difficult to constrain their mass distribution. So, yeah.
Gotcha. Um, so one of the questions that we get here in the planetarium a lot is sort of related to the formation of neutron stars and black holes.
Mhm.
So, about how long does it take to go from a star to a neutron star or a black hole? And do we see any like objects, or do we observe anything during that transition process?
So the question is, how long does it take for a massive star to, from its birth to form a neutron star or black hole?
Mm-hmm.
And do we see any intermediary stages? Yeah. Okay.
Yes.
So the main sequence lifetime for a massive star, as I said before, is about a few million to tens of millions of years. So it will deplete all the hydrogen in its core in that time. So very quick in an astronomical time scale.
Mm-hmm.
And then as an intermediate stage before it actually goes off in a supernova explosion, it creates a red supergiant. It starts expanding to a few hundred times the radius of the sun, and in at that stage, inside the core, you have subsequent nuclear synthesis going on, hydrogen to helium, helium to carbon, nitrogen, oxygen, until you form an iron core at the center of the star. All of that happens, I mean, very quickly compared to the main sequence lifetime, in less than a few 100,000 or less than a million years, and then it goes off in a supernova explosion. And when it goes off in a supernova explosion, you create a neutron star or a black hole.
Mm-hmm.
And at that very moment of the supernova explosion, that is where we are very uncertain of the physics, because if things fall on to a baby neutron star right at its formation, it could collapse and form a black hole.
Mm.
So there's a lot of uncertainty at that stage,
Mm-hmm.
but we know that massive stars evolve very rapidly. So yeah.
Gotcha. And I think we do have a question from the classroom. So,
Go ahead.
So, this is a silly question. So, how would the star evolution of your red giant that becomes this other big black hole, would that actually, help? Would you expect that also to go supernova or something? Would that affect into that red giant?
Thank you for that question. So, if I heard that correctly, you were asking about the evolution of the red giant in this system that I'm showing, the unicorn. So, red giants, they evolve very differently from red supergiants, the progenitors of supernova explosions and black holes. So, red giants, they again puff up, but they don't create supernova explosions. What they will do is they will expel their outer atmospheres and they will create a white dwarf. So what you could expect to happen for the unicorn, for example, you have a black hole right now and a red giant. Once the red giant evolves, it will, throw matter out, and the black hole will probably capture some of them. And this system might become an X-ray binary. There will be a very obvious X-ray accretion disk, and it will, eat the matter from the red giant, the expanding red giant. And the red giant will lose its outer atmosphere and it will become a white dwarf. So the final end stage for that system would be a black hole and a white dwarf in an orbit. So, great question. Thank you.
okay, if there are no more in the classroom, I just have one more question.
Absolutely.
So you mentioned at the start of your talk that we do see a very high peak in the frequency of about 1.4 solar mass neutron stars. Why do we see that like peak specifically at 1.4 solar masses?
That's a great question. So that's where you have to look at the something called the equation of state. Again, which is something that we're not very sure about, that defines the matter of highly condensed matter that's you see in neutron stars.
Mhm.
So the Chandrasekhar limit defines the maximum mass of a white dwarf.
Mhm.
So a white dwarf cannot be more massive than about 1.4 solar masses. But a neutron star can exist at 1.4 solar masses. So you won't see a lot of white dwarfs at 1.4 solar masses, but neutron stars can fill up that space very effectively because the white dwarf can collapse and create a neutron star after it exceeds the Chandrasekhar limit. So you see a lot of neutron stars around 1.4 solar masses. It's a very sharp peak and it drops off, and then you have a few at around 2.1 solar masses, but nothing more massive than that.
Gotcha. Thank you. Any other questions?
Have any other questions? Oh, we have one in the back there.
Yep.
You can speak up.
So I was confused with idea. But what exactly is time domain survey?
So, Dr.
yeah.
Vaccaro, I think you might need to help us out there.
Okay, sure. She's asking about like clarification generally. What is a time domain survey?
Okay, that is a great question. So a time domain survey is a survey that's designed to keep making repeated observations of certain parts of the sky. So we have, what do you call it, like a movie of the entire sky over time. So time domain surveys are a relatively new thing because you have to have a lot of technological backing to store the data. For example, the ASAS-SN survey that I talked about, we have collected 5 million images over 8 years now, and that data set it takes up about 1 petabyte of space. So what time domain surveys essentially do, they just focus on one part of the sky. They take data repeatedly at a set interval, and we can do that with photometry, spectroscopy, astrometry. It's just essentially repeated observations. That's a great question. Thank you.
We'll get another one in the back here. Go ahead.
Yeah, I was kind of curious, is there any theories as to why there's a big stellar gas gap that leads to the long time?
Were we able to hear that?
Yep, I think I heard that. So the question was, are there theories why we have this so-called low mass gap? That is a great question, and that is a topic of extreme debate amongst astronomers right now. And it's again got to do with the physics of supernova explosions. So if you have a protoneutron star right after a supernova explosion, and if matter can fall onto the neutron star and build up its mass, you would create a continuous distribution of masses from neutron stars leading up to black holes. But if there's some process that prohibits mass accretion onto the baby or the protoneutron star at its birth, you would have a cutoff. So you'll have a neutron star, but you can't put more mass onto it immediately. And then you will have systems where stars implode and form black holes. So you will have a gap because of that effect. So that is the current understanding of why there might be a low mass gap black hole. But recent discoveries like ours, we're finding more systems in the so-called mass gap. So it could just be an observational artifact. Maybe we are not observing enough systems to actually constrain the mass distribution. The answer to that question, I would say, will motivate a lot of research in the next decade or so.
Any other questions? Bob, you got a question. Really? Okay. I was just happy to see Phoebe. That was quite we took a Phoebe workshop this past summer, so your images of the movies of the orbiting stars with the radial velocity and light curves stacked on top of each other. We're seeing a lot of that this summer.
Yeah.
Oh, he's gonna ask one. Here we go.
So you have all this data from all the surveys, and it appears that there's actually a tremendous amount of work just to make one discovery, and those are potentially maybe doable. But a huge amount of data, so is there a way to expedite it or automate it so that it becomes more streamlined so you can make more discoveries?
Could you mind repeating that question, Dr. Vaccaro?
Sure. Yeah, he was just commenting on the large amount of data that you actually have. And of all that data, you only have 2 or 3 discoveries at this time. So is there some automation or streamlining of the process so that you can get more discoveries in a shorter amount of time?
That is an excellent question, and that actually forms part of my postdoc application cycle, where I'm actually trying to answer that question. So yeah, we can definitely have much larger candidate lists, but the problem is that follow-up observations are very expensive. Getting radial velocities is so expensive, and you have to apply for time. And since these systems are expected to have large orbital periods, you have to keep observing them over many hundreds of days, and you need to have telescopes that allow you to do that. So that's the bottleneck at the moment. We can get a lot of candidates, but to actually confirm and characterize them, that is a problem. But we're trying to tackle that systematically moving forward.
That's we do binary stars here too, and so that's something we're actually trying to work on now, is getting more radial velocities, and it's kind of challenging with the way observatories are run and geared towards really excluding the kind of things we'd like to do. It's almost like we need to have an observatory dedicated to spectroscopy of getting velocity for binaries, and exclude everybody else.
Yeah, absolutely, that's a real problem. You need to have a queue run observatory to actually put your targets in the queue, observe them at the right time. It's a difficult problem, and I really hope that there will be more facilities to do that kind of project in the future. And yeah, binary stars are really cool. Like Phoebe is a really neat tool, but to characterize systems very well, radial velocities are always the bottleneck. So.
All right. Well, if there aren't any other questions, let's just thank our speaker again for joining us today. And I guess we'll go ahead and turn it over to Greg, and you can kind of close us out here.
Yeah, so thank you for your talk, Tharindu. We really appreciate it. Thank you to everybody that's hung around with us for the talk. It's been awesome. So we just really appreciate you taking the time to talk to us, and we hope to see some of those updates here soon. So
yep, thank you so much. It was really great being here virtually, and thank you so much for your time.